Of course, we also have these hands-on sessions where you need to learn actually how to win the decathlon, and I hope that Nick will now tell you all about the next ongoing revolution actually. So that's an awesome title. As in background, Nick was doing his bachelor's and master's at the University of Minnesota, and now he's working at Amazon for the last 6 years already, and is really pushing on AutoGluon, having an awesome tool development. I always believe that we try to catch up with AutoGluon, and then Nick releases the next version of AutoGluon. We're thinking, okay, we have to get next version of our tools. So I think it's really an awesome stuff. And now it's all yours.
Awesome. Thank you so much, Marius, for the introduction. So super happy to be here today in person. Awesome. So yeah, super happy to be here today. Flew here all the way from Santa Clara, California, but yeah, it's been a pleasure so far, so really enjoying it. So today I'm here to talk to you about the AutoML revolution. Basically, the AutoML field is now about a decade old. AutoWeka, I believe, came out in 2013. Great work from Frank. And basically, since then, the AutoML field has been growing. We've been getting more and more sophisticated, and the tools have been getting more and more serious in terms of the engineering being put into them, in terms of the science being developed. So today I want to talk to you about the culmination of all of these things and where we stand in 2022. So let's get started. I am a senior software engineer, and I am a co-author of AutoGluon, and I am from Amazon AI. So we have a tutorial for this session. I made it very big font, so hopefully you'll be able to put it in. I would recommend to go here. I also linked it in this Slack group. And once you are there, my recommendation would be to use the Colab notebooks just to make sure that everything goes smoothly. You don't have to worry about any issues with your Python environment or whatever. So if you just load it up on Colab, and then the first cell, it will be a pip install of AutoGluon, and I would recommend that you just run that right now so that you don't have to wait for it to install when we actually get to the hands-on section of this talk. That would just be my personal recommendation for you. Okay, so with that, I'm going to move on. So ML in a nutshell, I like to think of machine learning in very simple terms, because generally speaking, when it comes to the average user that could benefit from machine learning, they don't really know all the complex stuff that's going on. So let's think about it from the very fundamentals. So you bring your data, right? Could be images, could be text, could be tabular, could be all of it at once. You throw it into something that uses your data somehow, that then is able to generate predictions that are useful for you. That is the core fundamentals of supervised learning for machine learning. So the question is, how do we make a system that is able to do this at the absolute peak possible performance while satisfying as many requirements from the user as possible? So let's talk about what I think are 7 steps to an AutoML revolution. Now, if you were here yesterday, you might have heard me in some of our conversations we had earlier on talking about how XGBoost is currently more popular. One algorithm, right? One fairly old algorithm. It's not even a neural network. It's not even some hyped up topic, XGBoost. It's more popular than every single AutoML system combined in terms of usage in industry. So really, I'm thinking about how can we make a system that basically is better than XGBoost in every dimension that you could possibly measure in terms of success. So let's get into it. 1, it needs to be easy to use and widely available. Just pip install, or available, runnable on your laptop, runnable on the cloud, runnable anywhere. It needs to have strong performance. Now, strong performance is an interesting question, because what does it mean to have strong performance? And I would say that it needs to push the boundaries of what someone would be able to do themselves without an AutoML tool, right? You need to be able to empower someone to make them be better at machine learning than if they didn't have AutoML. That's what I consider strong performance. And within that realm of strong performance, I want to push it as far as possible so that more and more people, right? Because maybe if someone's an extreme expert, then they could do better than AutoML, right? So I want to continue pushing that so that basically AutoML is stronger and stronger. Fast inference speed. So this one comes from an idea that I'm going to talk about a bit later of how oftentimes with AutoML systems, they generally rely on things like ensembling. And also there's a lot of technical complexity in terms of building an AutoML system, from the pre-processing of the data to the actually passing of the pre-processed data to your models, to then any post-processing you have to end up getting inference results to a user. And it needs to be fast. It needs to be fast enough to where they don't feel as if it's too sluggish for their use cases. You know, if you're in a production scenario and you have a system where when a user clicks a button, you need to take all of the information they just filled out in a form and make an ML prediction in real time, and they have to feel like this is something that's snappy, that this is something that is responsive, you better have a system that's fast. If it's not fast enough for them to feel like it's a good experience, then you did not create a successful system for them. So we need to keep this in mind. It needs to be stable and reliable. Again, if you aren't an ML expert and you get a seg fault or you get some crash, that's the end of it, right? That's the end for the most part. Now, maybe somebody will have the ambition to try to solve this problem, but a lot of the time people will just choose a different tool, right? We need to be extremely stable and reliable. We need to be able to handle large data sets with just very small amounts of memory, and we need to do it better than any other tool that isn't AutoML. We need to be customizable. We need to not just have one singular logic that is rigid and just is the only thing that happens. Maybe in future, there's a new model that is better than what we currently have in our AutoML system. We want to have custom model support to be able for people to add their model as a component to the system automatically. We want to be able to leverage the open source community to have them be able to add new functionality to the system so that it keeps on being and pushing the state of the art, so that whoever is the maintainer or owner, such as me, doesn't have to go crazy reading a billion papers and then trying to figure out what's the good things. Instead, the open source community can come, hey, I got an idea. This is a paper that I wrote, or this is an idea that I think works well. Here's a pull request. And then I just run a benchmark, click a button, and then I compare on hundreds or thousands of data sets, and I see, does this new component help in all the metrics that we would consider for success, right? So customizable and then also approachable in terms of a development side is very important. Interpretable. Now this is a very interesting topic that I could have a whole talk on, honestly, in terms of what does it really mean to be interpretable. But we can think of interpretability in terms of just giving the users confidence in why we did what we did, and also what things are important about their data. So for example, feature importance, Shapley values, things like that. Also, there are certain types of interpretable models, such as the iModels package, where you can literally print out the model into just one image with a couple optimized tree splits, for example, right? And so like we have custom model support. So the iModels author added iModels to AutoGluon, right? But it's something that we should think about, at least in the AutoML community, is how do we avoid people being scared off by the black box of AutoML? XGBoost is also black box, but we'll get into that. Okay, deployable. At the end of the day, you have your super awesome AutoML system. It gets super good accuracy. Amazing. You did it on your laptop, or you did it on some EC2 instance, you did it on something with a GPU. Now you need to deploy it on some kind of a system that actually makes predictions for you in your production use case. And that means that maybe that system doesn't have Python installed on it, or maybe it doesn't have your ideal Intel CPU or your NVIDIA GPU with CUDA installed, right? So you need to think about, how do you then take this artifact that you've created for your AutoML system and bring it to as many scenarios and deployment areas as possible so that you can actually solve people's problems. I think that if you solve all 7 of these to a strong extent, you do very well with them, that there is basically very little, if any, reason why you would not use AutoML. And basically then I think that the new standard is not oh, I have a new machine learning problem. Let me import XGBoost. So let me import Hugging Face or Torch or whatever. It's let me import AutoScikit-learn. Let me import H2O. Let me import AutoGluon. And that's like the starter point, right? That's like your baseline. And then when you just run that, it does its magic, right? It gets you a result. And then you can say, okay, look at the accuracy. Hey, that's good enough for my problem. Now I can move on with my life and do the next thing that's important that will provide business value. Or maybe now I can have time to actually engineer the pipeline of where I can process the data and put it into there instead of just working on models all the time. Or maybe I never had time to do this machine learning problem because machine learning is scary. I didn't have bandwidth, but I had this cool idea, but I just never had the time. Now I can just do AutoML. Hey, here's a proof of concept. What do you think, leadership? Oh, that's awesome. You like it? Cool. Let's productionize it. And now we've suddenly done something really innovative in our field, in the field that you're working in an industry, right? It opens up a lot of doors that previously are largely inaccessible just due to how much knowledge you need to even use XGBoost, honestly. So let's get into some more things. So what is AutoGluon? So AutoGluon is an AutoML toolkit that democratizes machine learning. It automatically builds accurate models for image, text, and tabular data with just one line of code. And it's open source and easy to customize, and you can get it just by pip install AutoGluon. Okay. And you can find our website at auto.gluon.ai. So we have about 200,000 downloads per month. Quite a few contributors. Feel free to check it out. And we're Apache 2.0 licensed, which means fully open source, no strings attached. All right. So let's talk about how AutoGluon relates to other work in AutoML. So prior work before AutoGluon came around was primarily focused, and I'm going to put an asterisk when I say primarily, not every system necessarily, but in general, the focus was on model plus hyperparameter selection, or the cache problem. Basically, given that you have a set of models and a set of hyperparameter ranges for them, try to tune and find the best model basically that satisfies your problem, and maybe do a little bit of light ensembling at the end of the day where you combine some of the best models together and get a better result. That was like the focus area of AutoML for a very long time. AutoGluon instead does something different. It relies on strategies that win prediction contests on sites like Kaggle through thoughtful data preprocessing, model ensembling via multi-layer stacking, a greater emphasis on modern deep learning techniques, and boatloads of tricks and optimizations. Let's get into this. What I would say probably one of the biggest differences is the multi-layer stacking. So let's talk a little bit about that. So hyperparameter tuning and AutoML were almost synonymous terms, I would say, for a long time. If you're in this room, you probably know the basics. Basically, you're trying to find hyperparameters values of a learning algorithm and produce the best model. You have a bunch of levers, right? And you're tweaking the levers all over the place, and these are giving you different values, and then you're just trying to find the one that gives you the best value. Awesome, fantastic. However, there are some problems with this. The biggest probably is that it requires many repeated model trainings, so it becomes expensive. Most of the models you're training are thrown away, and you don't actually use them in your final result because they probably were suboptimal hyperparameters and maybe didn't end up having good performance. The more hyperparameter tuning you do, the more your final model is overfit on the validation data, which is a very sneaky issue, by the way, right? Because if you just look at the oracle of what is the best model, you're like, oh, it keeps improving, amazing. But you'll never actually reach that oracle, because how could you ever choose it, right? It's because your validation scores, unless you're working with very large data, probably won't align perfectly with your test scores. And so by searching, you are giving yourself the opportunity to pick the wrong choice, or to trick yourself into, picking the model that has a lucky validation score, perhaps. And finally, it's less helpful when ensembling. And let me get into more on this final point. And by the way, there are hyperparameter tuning methods that are very good. And I'm going to talk a little bit about those as well. But just the basic idea of from scratch hyperparameter tuning for every problem, basically there's some drawbacks there. Okay, So introduction to ensembles, probably most of you know random forest. Pretty simple stuff, bread and butter. I love it. So basically, you know, it's just a bunch of random suboptimal decision trees smashed together and then you average it, which is amazing given that it's still extremely powerful and beats any state-of-the-art tabular neural network for the most part. Again, asterisks, you know, to date. So, you know, decision tree is just very simple. It's you make a bunch of binary decisions on your data for features, and then you split them into different groups. Then when you get to a leaf node for after you've done a bunch of splits, you just take the average, a label value of the data in that, and that's what you predict at the end of the day for new test data, right? And a random forest, again, is just a bunch of these averaged together. Cool, pretty simple. So let's take an example. Let's assume that we have this data. We're trying to predict the color of the dot. It's a regression problem. The lighter the color, the higher the value. And we have two features, X and Y, coordinates, okay? So this is what a decision tree would look like. It would make these splits and basically carve up the space based on these binary decisions it makes. Let's fill it in. This is what a decision tree would predict at any given point on new test data, right? And the thing to note here is that this is obviously better than random, right? But it's also suboptimal. You can see that there are harsh decision boundaries where the color from one pixel to another, right, will change drastically, right? It's not smooth. And here's a bunch of random decision tree, or not random, but like purposefully suboptimal decision trees trained on different subsets of the training data. And you know, they all, again, are better than random, but you can obviously see that they're not optimal. But the magic is that once you average them together, suddenly you do have a pretty smooth result, and this is a random forest. Now, what I find interesting is that if I hyperparameter tuned a decision tree to the end of time, right? If I just sat there in a for loop and I tuned the decision tree forever, it would, generally speaking, never be better than a default random forest. As in, a random forest, which is made up of an ensemble of bad decision trees, is fundamentally better than if you tuned to get the best decision tree. So one of the intuitions that I have as to why this is in this case is you can think that each decision tree is wrong, but it's wrong in random directions relative to the other decision trees. And so when you average it together, the reasons why they're wrong kind of cancel out. And so you get much closer to actually like the correct answer. You can also find this, there's some theories with humans in terms of averaging of human predictions as well. Like, you know, if you have the jelly bean like bin and you ask like 1,000 people how many jelly beans are in the bin, generally speaking, the average is much closer than any individual person. Right. So again, going back to the takeaways. So generally speaking, many models are better than few. And models that learn differently can boost accuracy even if they're worse in isolation. And hyperparameter tuning to find the best single model does not necessarily help find the best combination of models. Okay, so let's talk about origins of AutoGluon. So in 2018, so I worked at Amazon, right? And I entered this internal competition called the Scott Challenge 2018 with my good friend and coworker, Alex Shurkov, who is also on the AutoGluon team. And we didn't really have any expectations to win this competition. I wasn't even doing machine learning at the time, but I was like, you know, I really like machine learning. I'll throw my hat in the ring, see how we do. There's about 500 participants. And the problem was basically predicting if product A is the same as product B. So it's the product duplication problem on Amazon.com. And given that Amazon has 7 billion products, it's actually quite an important problem. Basically, the code that I ended up writing, you can kind of get a little bit of the scribbles there in the middle one, but it was an absolute mess. It was a nightmare. I don't ever want to look at that code again. But it won the competition by quite a large margin because I went crazy with it. The code was in like a monstrosity, but it was also very strong. And the thing is, this isn't an isolated case, and I'll get more into like the origins of things, but let's talk about other competitions. So how many of you, raise your hands, how many of you have heard of the Netflix prize? Okay, quite a few. So this is a famous, infamous competition. So simple goal, beat Netflix's baseline algorithm by 10%. Sounds, I mean, maybe it's easy, maybe it's impossible, who knows? Well, it turns out it took several years before anyone was able to actually win the competition, the $1 million prize. And the funny thing, if you read this quote here, is that the final solution was so complicated that Netflix didn't even use it. It was an actual nightmare to implement into production. Hundreds of machine learning models, all feeding their predictions into hundreds more machine learning models, all separated into like hundreds of script files of like saving autofill predictions into certain locations and then loading them in and all this ridiculous stuff, right? So I'm calling this a monster, right? In the sense that this is like the most powerful thing at the time that anyone was able to do, right? If they weren't holding back, this is $1 million, right? They got $1 million for this. But the monster was untamable. It was wild, right? And this is an isolated case. The evolution of monsters, Kaggle. Good old Kaggle. So Kaggle, as you probably know, is a ML competition site for real money, where companies or whoever really just has the problem, they put a prize bounty for it, they hold a competition, and whoever gets the best metric score at the end wins and gets the money. These are all first place real money competition wins of competitions of over $100,000. These are all hundreds of machine learning models all ensembled together in something called a multi-layer stack ensemble, which is very much a pain to implement. And I would call all of these monsters in a sense, right? They're, again, the most powerful thing that anyone could have done at the time, pretty much, or the most powerful thing. But also, holy shit. Imagine you're the engineer, like you don't know much about machine learning, and then your boss comes up to you, hey, we did this competition, here's the winner, can you implement that? I don't know. I don't know about that. Imagine whoever implements this then leaves the company. Who's going to debug it? Huh? Who's going to be the person that does the business report on the performance regression on this thing and proposes solutions to fix it, right? It's not going to be a fun time. And that's not even talking about the inference speed. Let's not even talk about that. Okay. So my question, can we tame the monsters? So can we make them reliably performant, stable, and sensible to countless different data sets? Can we assemble them in an appropriate manner without need for expert knowledge from the user? Can we train them in a reasonable amount of time on a wide variety of hardware? Enable flexibility to satisfy user constraints? High complexity behind an elegant API, which is probably the most important point as well. I would say that AutoGluon strives to achieve these goals, and I think that as of 2022, I think that we have achieved these goals. So let's get into that. So in 2020, we had our first paper where we showcased performance, basically, of AutoGluon. And basically, we were able to show that we beat the best in hindsight combination of all existing AutoML systems at the time. So this, and I will talk a little bit more about the things that we did to achieve these results in terms of the techniques. But this was in 2020, right? And so this was on the AutoML benchmark plus Kaggle benchmark. And another thing we showed is that out of 2 of the 11 Kaggle datasets that we tried, we were able to get top 1% human private leaderboard scores in 4 hours of CPU compute. So this was 2020, but we've made a lot of improvements since then. I will also say in 2020, we had a serious inference speed problem. Basically, the monsters were not fully tamed at this point. They functioned, but yeah, expensive. So now 2022, where are we at? So all of these results are from an independent paper and analysis done by Peter and actually members of H2O, I believe, the authors of the AutoML benchmark, where they compare all existing basically modern AutoML systems. So the menu post hoc test, this is basically the rank. So rank of 1 means that you are first place on a data set. Rank of 2 means you're second, third, fourth, fifth, all the way. And then basically this is the average across 104 data sets in the AutoML benchmark. And AutoGluon is statistically significantly ahead of the other system, which are largely grouped very closely to each other. Another is, this is a chart of basically the scale performance, -1 being a tuned random -1 being a random forest model, and 0 being the optimal performance on a given data set, again, averaged across 104 data sets. And what we can see it's the leftmost of the frameworks is AutoGluon, and AutoGluon very consistently is able to beat random forest, basically be able to be better than -1, and in a lot of cases be very, very close to 0 in general, especially in multi-class classification where multi-layer stack ensembling is most strong, basically. Another aspect is stability and robustness. Again, going back to that this tool needs to work. It needs to not crash. And with AutoGluon, we have a 99.86% success rate on, so basically 3 failures in 2,080 data sets in the AutoML benchmark. And the 3 errors that we did have were memory errors. So basically, if you have more than 32 gigabytes of memory, you probably wouldn't have those errors. But yeah, so this is another thing about stability and making sure the system works well. So the other aspect here is about inference speed, you might be thinking. So a common concern with AutoML is, will it be slow to infer? How can I control the inference speed? So in a newer version of AutoGluon, so in 0.4, we added this infer limit logic. We're basically given an infer limit, which is basically the speed per row that you want AutoGluon to be able to predict at, as well as the batch size, so basically how many rows of data to send in batch to achieve that infer limit throughput. These are constraints that AutoGluon will then satisfy, and it will automatically adapt its training strategy to satisfy the constraint. And so here we see a comparison graph of quality, so accuracy basically, and inference speed. And so if you see the 5 dots marked in red with red arrows, these are different configurations of AutoGluon with different infer speed preset, or with different infer limit values, basically. And this will help to control basically naturally to preference models that have faster inference speed during training. And so by just playing around with this one parameter, basically, you can then basically expand the Pareto frontier of solutions within the inference speed accuracy trade-off space. The other thing that I want to note about inference speed is that you can see in the very bottom, I have a comparison where I don't just show you the number of rows per second, I also tell you how many dollars it costs. So how many millions of rows can you predict per dollar? Basically, if you were, say, using an EC2 instance on M5.2x on AWS, for example. And what we can see is that modern AutoML tools, so AutoGluon's best quality, which is the one in the top right, that's the monster for sure. But even that, 4 million rows of data per dollar, right? A lot of scenarios, that's actually pretty reasonable, especially if your data if it's important that you want high accuracy for your data. And then on the other end, you could get 400 million rows per dollar with, by just changing the setting and then getting pretty strong results still. Now, I want to focus in on specifically the Pareto frontier now, and I want to also now include our, the very commonly used baseline models, not AutoML. So remember XGBoost? Well, here we go. So we have XGBoost, LightGBM, and CatBoost here, which are basically the exemplary individual models that people would perhaps use. And what we can see, first of all, of the base models, if you're using XGBoost, I would recommend CatBoost. CatBoost is very good. is what I'll say first. But otherwise, what you can notice is that if you're okay with spending $1 per 400 million rows of inference, or $1 per 40 million rows of inference, then you're leaving a lot of quality on the table by choosing to use just a singular model like XGBoost or CatBoost or LightGBM. If you use an AutoML framework, basically any AutoML framework, but with AutoGluon particularly highlighted here, you can get a lot of performance improvement. And I will say, by the way, just to understand this scale, 1.0 for accuracy is basically if you take the best score on a data set for all the frameworks present here in this list, and you assign it a score of 1, you take the worst one and you assign it a score of 0, and then you average across all the data sets. That's what this is. So basically, like AutoGluon best quality is within 10% relative of the best solution found on a data set on average than within the worst solution found on the data set on average, basically. You can think of it that way. Okay, and then what about, so this is just comparing across AutoML systems and singular models, but are those even competitive with people, right? Like, is this even a relevant graph? Is this the thing that we should be comparing against? Well, let's talk about comparing against people, specifically people that enter machine learning competitions. So we are able to get quite strong results with the certain amount of code that I will reveal to you pretty soon in terms of what we do. All of these competitions use the exact same lines of code that we send in, and we get then these results with just about 4 hours of CPU or GPU, depending if it's like a text or image-based problem, we would use GPU. I will note that for the data sets marked in prior to 2021, these are not live competition ones. We submitted after the fact. I just want to make that clarification. But generally speaking, it's still representative of how strong it would be. Just we might have benefit of new technologies and whatever. Okay. Still, they're very strong results. Okay. So, and to highlight this for the Auto Group competition, so this had over 3,500 teams compete. And in 4 hours, AutoGluon achieved a score that took the best team over 2 months to beat on Kaggle. And this solution that AutoGluon created in 4 hours achieved rank 14 on the final private leaderboard, which is Kaggle Gold, also known as one of the prerequisites to become a Kaggle Grandmaster. And so just think about the utility of that, right, from a system. Imagine if AutoML can achieve this on a regular basis. Again, if you're talking about a business, right, if you're talking about somebody in industry, they are not going to make a solution as strong as the team that took over 2 months to beat this on Kaggle for their arbitrary problem. They're not going to do that much work, right? Kaggle has all of these things that make it so that it's extremely competitive, right? You have all of these discussions happening. People are sharing ideas. They're sharing all these notebooks about feature engineering tricks. They're doing all this stuff, right? That's not the case in industry generally. Generally, it's, you and maybe a couple other people have to solve this very specific problem, and maybe you don't have maybe you aren't a Kaggle Grandmaster, or maybe you just don't have that kind of a background, or maybe you don't have 2 months to just work solely on this. You need other things to do, right? So think about being able to get that kind of quality, but without needing to know anything and just in 4 hours, right? So how did we do all this, right? Well, we did not hyperparameter tune at all. We used the same hyperparameters for every problem. We use near default hyperparameters for all of our models. And we trained using the same 3 lines of code for every problem. Import tabular predictor from AutoGluon.tabular. Predictor equals tabular predictor. Specify the label column, class, for example. Specify your training data. You can also pass a pandas data frame. Specify the preset, for example, best quality, which basically cares most about getting high quality performance. And specify your time limit. Do you want it in a minute, 10 minutes, an hour, 10 hours, weekend, right? Just let it go. Come back to it when it's done, and you have your model. Now you have your fit predictor. It's saved to disk. And you can also just call predictor.predict, pass in your test data. It could also be a pandas data frame. there you go, on with your day. There's your production system. Save the artifact, upload it to a new machine, install AutoGluon, let it run. That is, as simple as I could think of how to make it, basically. If anyone has ideas on how to make it simpler, I would be happy to hear. So again, how do we do this, right? How do we avoid having to hyperparameter tune, and still get strong results? Well, we have a large number of models implemented and optimized out of the box, such as the classics, XGBoost, LightGBM, and CatBoost, custom tabular neural networks that we've implemented, scikit-learn, random forest, structured trees, KNN, state-of-the-art image models such as EfficientNet, ResNet, also all of the TIM library or the PyTorch image models library, basically, we've integrated that. Yeah, so any TIM compatible model. State-of-the-art text models, BERT, Electra, also any all of Hugging Face. We've integrated Hugging Face, compatible. And so we take all of these models. Now, maybe not all of them are relevant to every problem, right? You probably wouldn't use an image model if it's, just a tabular problem. But, basically we pick all the models that are sensible for the data set. And then we do something, it's called bagging. If you're familiar with the concept of cross-validation, it's very, very similar to that. Basically, you take your whole data set, so your complete data. I'm not even talking about validation here. So there's no such thing as validation. Just think of, you have data that has labels that you can use to train that to help improve your test results. So you have all that data. You split it up into, let's say, 5 folds of 80-20 splits. You use 80% of your data as training. You train a model with 20%, with the remaining 20% as validation. You do this across all of your data so that if you look at the right-hand side, every row of your original data was validation data at one point. And this is the golden aspect of this. This is called out-of-fold predictions. So you see what these validation predictions are, you can think of as unbiased prediction probabilities of the given model if it were trained. So basically you can think of it like this is what this model would have predicted if it saw this row at test time, is kind of an idea of what you're thinking here. And this is a feature. This is automated feature engineering. You can now use this feature, concatenate it with your original data, and train a new model. And now you would have a LightGBM model that sees what CatBoost would have predicted for this row as a feature, or what KNN would have predicted, or a neural network. Or maybe you'll have a neural network that sees what LightGBM would have predicted, or CatBoost, or another neural network would have predicted. These are very powerful features often. And this leads me to multi-layer stack ensembling. So you may have heard some of the other systems earlier in this talk about how they have stack ensembling. So there's basically, there's one layer stack ensembling, and then there's multi-layer stack ensembling. So with one layer stack ensembling, basically you generate these out-of-fold predictions. You don't have to do cross-validation though. You can just use holdout, and then basically you generate that final stacker model. But this, in multi-layer stacking, basically you have a whole nother layer of stacker models, and then you can repeat the process. You can have as many stack layers as you want, and basically you can think of it as a neural network. You're fitting a neural network layer-wise, and instead of perceptrons as the unit of the neurons, it is entire machine learning models. So instead of a perceptron, it is LightGBM, it is CatBoost, it is XGBoost, it is an entire another neural network, and basically they're able to feed their knowledge into other models to empower them. And so this is basically the most popular technique on Kaggle. If you go to Kaggle, you look at winning solutions, they're probably using stack ensembling. It's just what it is. So this is a very powerful technique. If you'd like to learn more about this, you can refer to our paper, which is also linked in the tutorial documentation here. But yeah, this is like an in-depth topic. I'm not going to go too long into it because I have a lot of slides to cover. Okay, cool. So let's talk about not only the state of like where AutoML is, but also the rate at which it's improving, because I think that that's also an important point to think about, right? Because if AutoML is doing well, but there are other systems that basically, or like other things that aren't AutoML that are improving faster than AutoML, then maybe AutoML isn't the future. So let's talk about that. So in March of 2021, AutoGluon version 0.1 released. It had a greater than 70% win rate versus its prior release, 0.0.15, including adding of multimodal tabular plus text support, fast AI tabular neural network, and it added XGBoost. 0.2 in May of 2021 had a 53% win versus 0.1, 4 times faster inference speed, 10 times less disk usage, and integration with NVIDIA Rapids for GPUs. 0.3 in August, 58% win rate, 2 to 10x faster online inference, which includes basically sub 20 millisecond end-to-end latency. Multimodal tabular plus text plus image support, now we got all three. Talk more about that in a bit. Integration with PyTorch image models, or the TIM library, and custom model support. Version 0.4, March 2022, 63% win rate versus 0.3, 93% win rate on large data sets, 30% faster inference speed, 2 to 3 times faster training speed via parallel bagging with Ray, as well as the infer limit argument that I previously mentioned. We added automated temperature scaling calibration to our models. We added Windows support and cloud training and deployment via SageMaker. 0.5 in June 2022, we have another 2.5 times faster inference speed. We added time series support, and we added multimodal transformer support. So that's a fair amount of things. Now, XGBoost also improved, but you want to know the magic? AutoGluon uses XGBoost. So if XGBoost improves, then AutoGluon improves. If LightGBM improves, then AutoGluon improves. If CapBoost improves, then AutoGluon improves. If someone creates some new fancy model that absolutely blasts XGBoost out of the water, we'll add it, and then AutoGluon improves. So you can think that AutoML is the combination of the best of open source. And then we add in all of our little tricks and optimizations, meta learning, HPO, stacking, ensembling on top of that to create something that's just better, improves it, right? And then we just add all of our ease of use things on top of it, and we're good to go. So in that sense, as long as we provide the tooling available for people to add their models and their systems and their improvements to the AutoML system, and we just keep it up to date and we keep, making sure that we represent the best of the open source community, we can continue to have very, very strong results and improve. So speaking of improvement, this is that previous graph, now just with AutoGluon, but via different versions. So we can see AutoGluon version 0.1 in the farthest right here, and then AutoGluon version 0.3, and then AutoGluon version 0.5. And then those dots to the left side are just AutoGluon version 0.5, but with different infer limit specified. So basically more fast ones. Interesting thing is that basically from going from version 0.1 to version 0.5, if we try to equalize accuracy between them, we get over 100 times faster inference speed than what the best that we were able to achieve in version 0.1. If we just relax version 0.5 to match it, we get 100 times faster inference speed. That's what we get in 1 year, right? So I would say that that's pretty good progress in terms of practical usability. And by the way, we aren't even compiling the models yet. That'll give us like another 10x. So we're planning on doing that soon. So yeah. Okay. Now interpretability, right? This is another important point. So we have feature importance by permutation shuffling. So permutation shuffling is a generalized feature importance logic that's quite good. If you want to learn more about why it's good and better than model-specific versions of feature importance, you can look up Jeremy Howard's very detailed talk on this topic. You basically just Google Jeremy Howard permutation importance. There's a very nice blog on it. I would recommend it. And also we have built-in kernel SHAP support and iModels package integration, which is interpretable models. We also have a cheat sheet. So this is everything you need to know about how to go from knowing nothing about machine learning to training and deploying a multi-layer stack ensemble. Yep. So feel free to peruse this. It's also on our website. But yeah, again, trying to make it in as few lines of code as possible. And yeah, just really get to the core of the people's problems to solve them. All right. So before we jump into the hands-on portion, I want to do a quick Q&A. Does anyone have any questions so far?
what are the chances to have support for other formats of input data, such as sound or graph data?
Great question. I'll cover that in a little bit in the portion after the hands-on. But basically, we do have plans for that. Yes.
So thank you very much. I wanted to ask about the interpretability stuff again. Sure that rotation shuffling is nice, and SHAP in general is also model agnostic, right? And there are a bunch of other model agnostic techniques. Why are you aiming now for or advertising actually permutation shuffling in the first place? Because all of these give you different kind of insights, right? It's not like it's only that you would like to know about feature importance, but also effects and so on. And it always depends on the stakeholder, right?
Sure. And what I'd say there is, you bring up a good point. Is why would you specifically highlight permutation shuffling over missing value, indication, or whatever other kinds of information about the data, right?
Yeah.
So we are creating AutoGluon.EDA, exploratory data analysis, which is going to be automated exploratory data analysis that basically tries to do a whole bunch of things to gain insights about the data, and then basically figure out heuristic logic to rank the importance of things when it comes to showcasing to the users what's important about their data, such as anomalies, missing values, ambiguities about feature types, as well as things like feature importance and feature correlation. But yeah, it's a very in-depth topic, I would say. So I don't really have too much about it for these slides. We talked about it in depth at KDD 2022, where we had 3 hours. But yeah, I had to cut those slides.
Yeah, thanks very much. Great vision. I very much share it. I had one question. So you mentioned, well, if there's all kinds of new methods, you'll just put them in. You get better performance. You can have tooling for other people to add stuff. At some point, that does become a monster too. And you also mentioned one of the things that makes AutoGluon tick is boatloads of tricks and optimizations. And how automated are those? And I think they're not very automated. And what happens if you leave?
Fantastic question. I think about this a lot. So I could talk about this probably for an entire day, because this is on my mind. So I'm the lead developer of AutoGluon. I lead a team of 10 people, including an additional 5 or 6 interns. The team is growing, right? We have collaborations with all these different teams within Amazon, and also external teams. Like we have collaborations with NVIDIA, with Intel, with all this stuff, right? All this stuff is going on, and I kind of have to keep it in my head and try to make sense of everything. And I need to be the person that says no to people when they want to add something and it doesn't quite meet the bar, right? And that's tough, right? It's a tough place to be in. And you're right. Basically, a lot of the tricks, they aren't automated in the sense that like we automatically found them somehow, right? It was pure dedicated knowledge of things that worked elsewhere and incorporating them into the system in an intelligent way, right? And this is something that I don't think can realistically be automated anytime soon, right? I mean, anyone feel free to prove me wrong, but there's a lot of subtlety that goes into the engineering of the system, right? When you go from theory to practice, you have to build a system that provides logs that make sense to users at appropriate times, is able to not crash, is able to be simple enough that people can code it other than me, right? like basically the person who authored the code, someone else can then go and edit that code, right? It needs to like have some kind of structure that, isn't ridiculously complicated, right? And so you have to then make all these kind of trade-offs in terms of practical usability versus, in theory, what would be the optimal. And this also includes how much time you have available in terms of development, in terms of the fact that there's low-hanging fruit everywhere in AutoML. And if you just spend all your time on one thing, then eventually it's not going to be low-hanging fruit anymore, and you could really use your time better spent elsewhere. I don't know if I answered your question, but maybe I just added more questions. But yeah, there's a lot of subtlety to developing an AutoML system.
Maybe you follow up and bring back to the next question. You said it can't be automated. Meta learned if you have,
Oh, okay,
Amazon has
sure,
so much
sure.
data.
I mean, again, it depends on what techniques we're talking about, right? If we're talking about, for example, like one trick is, adding adaptive early stopping. Like, okay, theoretically, maybe we had some, like basically you need to know to search for that to begin with if you're talking about like meta learning it, right? You need, like, to implement it is, like, you first need to implement it to be able to search it, right? And so, like, yes, like when you implement the tricks, then the logic of how do you kind of assemble what is the appropriate tricks to use in combination with each other can definitely be automated, right? You can do this huge sweep of saying this on, this off, this on, this off, or this with this configuration, and then meta learn something, right? Or do zero shot. And that's actually what I'm working on right now. I'm working on doing zero shot optimization of our model hyperparameters. Remember how I said all of our hyperparameters are just like the default hyperparameters? It's because when I created the system, I basically just set them as the defaults. It worked super well. And I'm like, well, I don't want to mess this up. So, I don't want to like overfit to like my understanding of like what we're doing on whatever data sets. I'm like, you know what, it's fine. But like, yes, we can improve by tuning these things, right? And doing it the traditional way where you just from scratch do it on every data set, is very expensive basically. And so looking into alternative smarter ways like zero shot meta learning, I think is the future for that kind of stuff. And that's the stuff that I've just started looking into basically. And I think is very promising, but yeah. I think let's do one more question. I know this mini Q&A is not so mini anymore, but okay.
About the stacking part, do you do hyperparameters in that? Do you change the stacking for different things, or it's also a default stacking approach?
Yeah, so
quickly, can you repeat the question? It was not audible.
Oh yeah, sorry. The question was, do you hyperparameter tune the stacking component, or like do you adjust basically the stacking logic? So the answer is, for the most part, it's fixed. So you can think that the search space of a multi-layer stack ensemble is ridiculous. You can think of it, it's like neural architecture search almost, where you can fit an arbitrary number of layers and you can fit arbitrary models at each layer, right? And you can't even optimize it all at once like you can with neural architecture search, right? There's no backprop where you can then go back and say, oh, whoops, I'm gonna adjust the first layer models once you've trained them. You would like, it's kind of complicated basically. So I haven't really done a whole lot of optimization in terms of what's the optimal multi-layer stack configuration. So I do something super simple. I just know that there is a list of good base models, and then I just use the exact same models in the further stack layers. I just assume, okay, we're doing a machine learning problem, right? We just added new features, right, with the stack layer. So it's the same data, it's just with new features. So I need strong generalized machine learning predictor models. Okay, I'm just going to use the ones that I already picked earlier that are strong generalized predictor models. So just use the models with the same hyperparameters, right? And then in terms of like how many folds and stuff, I use 8 k-fold. The reason I use 8 is because generally speaking, CPUs come in factors or in multiples of 8 for machines. And so when we parallelize, we can then neatly, if someone has 8 CPUs, we can neatly train 8 folds at once, giving each one CPU, which is very nice. And yeah, in terms of the number of layers, I just did 2 layers because it worked quite well, and because there's this whole really complicated stack information leakage problem that happens if, and whatever, I'm not going to get into it. Leonard knows what I'm talking about. So yeah, anyways, that would be the answer. But I think we would probably want to move on because the mini Q&A is not mini. Okay, but yeah, thanks everyone for the questions. So now let's do about a 15 minutes hands-on tutorial. So again, I would recommend going to the GitHub. I would recommend working with a group of 3 to 5 or so, and just go through the tabular quick start tutorial, make your life easier. I would recommend just using Google Colab. If you want to give it a try by installing it on your machine, feel free to. It works on Windows, Mac, and Linux, but again, just within the 15 minutes time span, you better like just using Colab. So yeah, I'll let you know when 15 minutes has passed. Feel free to ask me any questions. If you want to just raise your hand if you have any questions, I can come over. Thanks. All right. So it's been about 15 minutes. Thanks everybody for going through the tutorials and asking all the questions. I'm super happy to hear that there's a lot of interest. So feel free to continue doing this whenever you'd like. But I do have more stuff to cover because there's a lot of stuff we're doing in AutoGluon. So let's get into it. I know that we have about 10 minutes or so left here technically. We'll see if we'll see. Okay, so part 2, multimodal AutoML. So multiple problems. For example, is a Kickstarter going to get funding or not? Is it going to pass its goal? Right? You have the text of the entire Kickstarter project. You have the goal in dollars. You have what country it's from, currency. Right? How do you solve this problem? Right? This is not just tabular, but it's also text data. Or predicting if a pet is adopted or not. You have a website on a rescue shelter site, and there's an animal's web page, and it's a picture or pictures of the animal, plus things like what metadata like age of the animal or name. There could also be the text description of the animal from whoever brought the animal into the shelter, right? And then you need to predict how long is it going to take for the animal to get adopted, right? And then, for example, with this algorithm, you can look at the animals that are predicted to not be adopted anytime soon, and you can then try to improve their websites so that they're more appealing, so that that animal gets adopted and finds a home, right? And this is multimodal in nature, right? Because all the different aspects are important. And you somehow need to create a model that captures all these different modalities of data at once and uses them in tandem. So, yeah, again, as I said, you have the image, you have the text, you have tabular, and you need to predict how fast they're going to be adopted, right? So, at Amazon, this is a very, very relevant kind of task. Is it the same product or not? Remember that Scott Grant Challenge 2018 that I participated in, right? This problem, is it the same product or not? Given, let's say we have an image of a new product that's uploaded and then the store page of an existing product, is it the same or not, right? You could incorporate a bunch of different information, or maybe there's 2 product pages and then you need to compare all this information together. 2 different shirts, right? So how do we do this? So now, instead of your data just being tabular data, it's data that contains image, text, and tabular features. And with AutoGluon, you can call predictor.fit on that data, and you can then deploy it. Same exact lines of code. We automatically handle multimodal data. So this is what it looks like. Your images, so first the summary column in blue, this is text. This fits directly into a CSV or Parquet file, whatever data frame. So we don't even really need to change our format. That's pretty standard. And then we just have logic that automatically detects if this is a text column or not. You can have some very basic heuristics that are very effective, such as if you do string.split over spaces, what is the length? What is the average length of the list that you get? And if it's like greater than 3, then it's very likely text. Or you can do something more fancy, but again, not too hard to at least detect that it's text. For images, we currently have the user specify that this is an image column just so that we don't do anything weird. But basically, this is just path to disk of the image, right? And so then basically given this kitchen.jpg, we can then load that image from disk and then we can use it in our training or prediction, right? And then we have all of our tabular values and then we have the label, right? And so with this representation of the data, we can input multimodal data directly in. And now we just need the magic of how the hell are you going to train a model that uses all this, right? So let's answer that question. So this slide might be jumping ahead of the game a little bit, but here we go. So again, in 3 lines of code, it's just instead of from AutoGluon.tabular, now it's from AutoGluon.multimodal. Import multimodal predictor, and then same deal, specify your label, pass the fit data, call predict, and then if you want to auto ensemble with the tabular models as well, you can then run tabular predictor in multimodal hyperparameter mode. And this will then do a multi-layer stack ensemble of basically like ResNet, BERT, like a ResNet image model, a BERT language model, and all like the tabular models together. So the fun thing about a multi-layer stack ensemble is that it's kind of like the glue that brings all the models together, right? So you can think of it that, remember how I said like multi-layer stack ensembling allows you to have a model that sees what another model sees in the sense, right? It lets you see, okay, this is what this model would have predicted. Now you can have a CapBoost model or light GBM model that sees what ResNet would have predicted given the image, or sees what BERT would have predicted given the text, right? And so then these models can now incorporate that information in to make a decision. So how good does this do? Very good. We're able to get multiple first and second place solutions on very competitive competitions with this. Again, 3 lines of code. And yeah, top 1% on a live competition, KO Pet Finder popularity contest, which just happened basically. So this a live competition, 3 lines of code, top 1%. So what happened within these 3 lines of code? So we have pre-trained image and text models that we pull from various open source model zoos. Then we do multimodal fusion and other training tricks, and then we do automated multi-layer stack ensembling, which is covered, in the prior part. So foundation models you might be familiar with. These are all the hype and rage nowadays: Roberta, Electra, GPT-3, all that good stuff, right? How do we leverage these things? Well, there's a whole ton of them on Hugging Face, greater than 60,000, and a lot on Tim as well. However, most AutoML tools don't really leverage these model zoos. They mostly are focused on tabular. So AutoML for image and text data is still fairly new. There's a couple packages that do it, but generally speaking, it's not as well developed as tabular. But there's these existing very powerful pre-trained models that you can leverage for this. And so questions are, how can we use these foundation models? How we combine them with the other tabular models that we have. So we did a benchmark. We brought together all of these different data sets, which are multimodal data sets. And these are very relevant kinds of problems. So predict the sentiment of a user associated with a product review, predict the salary range of a data scientist, price the label of an Airbnb, right? Customer review score for clothing, sale price of houses in California, all this kind of stuff, right? And this is a paper that we have published in NeurIPS in 2021. Okay, so we have different fusion strategies for how we can make these transformer models architectures work in a multimodal setting. So we have all text fusion, where we just basically concatenate all of our tabular data as if it was text and then treat it as text and pass it into a text model. That's A. We have early fusion, where basically we do all of these different, I probably don't have time to get into the difference between early fusion, late fusion. Basically, we have different embedding heads and transformer heads that then move into the main logic and aggregate together. Anyways, yeah, you can read up about the details in our paper. And then once we have this multimodal net, that's basically this aggregation of these multimodal data, we can then incorporate it in with the tabular models via several options. So one popular option that you might know about is embeddings, right? Embeddings is a very popular one where, you have this pre-trained model or whatever, and then you generate an embedding on your text data, and then you pass this into your tabular model, and then it gets some information from it, right? That's a very popular option in industry, by the way. It's very widely used. We have the weighted ensemble, which is pretty straightforward. If you have your multimodal net, then you just have some tabular models on just tabular, then you weight them together. Maybe you'll do better than any one individually. Then you have the good old stack ensemble that AutoGluon has, and basically, right, because AutoGluon's stack ensembling logic is modular, we can just chuck in multimodal net as another base model, and off we go. Fantastic, right? So how does this work out? Okay, so first thing, yeah, we have like layer-wise learning rate decay and average topic. You can check our paper. Okay, so first we choose the backbone for the text. And so we found that Electra with some exponential decay and averaging through checkpoints works well. So we choose this as our baseline one that we train for text. Then we use a fuse late strategy from basically all text, fuse early, fuse late. We choose fuse late. And then okay, how good is like doing embeddings versus doing weighted ensembling versus stack ensembling? Interestingly, embeddings are very, very bad compared to ensembling. So if ever you are in a scenario where you could have your original text model and basically ensemble it with your tabular models, you should do that, generally speaking, instead of extracting embeddings from that text model and passing it to the tabular model. We found that this is better. And then stack ensembling is even better than the weighted ensembling. As we found, generally speaking, stack ensembling is better than weighted ensembling, so it's not so surprising. But basically, this is the thing that we found that works very well. And then this is basically, you know, how it works, right? So we take image data from, you know, OpenAI, Tim, Clip, and then tabular data with FG Transformer, text data from Hugging Face, and then we do this fusion, this early fusion logic, or I think late fusion logic. And then that's how we generate upload, and that's our multimodal net. And yeah, so again, this is Kaggle, second place in this competition. That's the code to make it happen. And that's without the ensemble. That's without using the multi-layer stack ensemble. That's just the multimodal net. So second place, product sentiment classification. This is first place in 3 lines of code. This one, Finder popularity. This one was 20th place out of 2,537 teams. This was live. We also, this is a competition that just ended a month ago. So this is 15 minutes left to go in the competition before it ends. You can see that the top scoring public notebook is AutoGluon with 3 lines of code. So then this was copied by about 300 people in the competition, and then they submitted this as their final result. But yeah, and notice, if you see the names of the things that did worse than this, we have Huge Ensemble as second place, Transformers plus GBM Ensemble, Roberta Base plus Large Roberta. These are not trivial notebooks, I don't think. You know, this is like stuff probably that you're new to, you know, brand fresh new to machine learning person in industry setting probably won't be doing. So again, out of the box performance. Some more competition results. We got first place in predicting data science for India. We got second place in predicting the price of books. We got second place in predicting California house prices. Yeah, and we have a whole bunch of tutorials for multimodal. I don't have time for this one because this is the stuff that we do for a 3-hour session, but this is 90 minutes, so you know. But yeah, and basically, let me see if I have any other slides. I think I have. Yeah, that's ambitious if we're going to get there. But so yeah, and by the way, I've already kind of mentioned this, but AutoGluon's fully open source. We're welcome to contributors from anyone. Anyone's feel free to send a pull request or email us, you know, or open a GitHub issue. More than happy to you know, work together on improving the state of AutoML. Yeah, and I guess the next part would be like talking about time series and stuff, but that's very ambitious if we're going to get there. So I think, what do we want to do, since we're technically, we started a bit late, now we're a little bit over. Do we want to do a final Q&A maybe, or?
5 minutes, I think, could be fine. Yeah.
Okay, gotcha. All right, Q&A. All right.
So thanks for the great presentation. If you would spend a bit more time and compute on these competitions, do you think AutoGluon, also if you enable multi-level stacking, could actually become first place in every of them, or is there something more?
I think that it's possible, yes. So a lot of the ones that I showed was like interns basically giving it a go on things. I think that if we enabled all the things that AutoGluon had to offer and we really tried, I think we could potentially get first on one of them. It's very hard sometimes though, because these competitions are very competitive. But I do think it's possible. I mean, so like, to be clear, best quality of AutoGluon is not actually everything turned on. It's more or less like everything that is within what I consider reasonable turned on. But we have other things like automated semi-supervised learning, automated feature pruning, and also like FG transformer and like more expensive models that aren't enabled in best quality even, right? So like if we really wanted like a competition quality, I guess you could call it, we could push it further, and it would be interesting to look into that. Yeah, but it's an open question, really. I think if we are able to achieve that, it would be awesome.
Yeah, so we actually thought about using AutoGluon in competitions, but I thought there was something that you're not allowed to use AutoML anymore.
I hope not.
That's why we didn't do it. But you don't know any of that? Maybe
I'm not so sure on that regard. I will say. I remember a while ago there was this whole idea where they had like the Google AutoML thing was like something was going to be like a baseline for KO competition. I remember that. I don't know what happened with that, basically. But
yeah, that's basically when we stopped it.
Yeah, I mean, honestly, I would say as long as we aren't in the money, then probably it's okay. But like if like we get like first place, then maybe there's something.
And you can decline it.
Maybe, yeah. I don't know the nuances of all that, but yeah.
I mean, it would be great motivation for students and so on. If they could even prize money.
Right.
I'm not sure whether.
But I mean, here's the thing. Maybe not us doing it, but someone else could import AutoGluon and run it, right? So potentially.
Yeah, but I think it's sort of in general not allowed. But,
sure. I mean,
or there was something about it.
Maybe we could chat later on it, but
it sort of doesn't make sense. Where does AutoML stop?
Yeah.
If XG was optimized, was HPO, is that AutoML or not?
Right.
How is this not the monster when you're using GPT-3 for multimodal?
Sorry, can you say that again?
How is this not the monster type of system when you're using GPT-3?
Okay, so GPT-3 is a model that we could use if someone said use GPT-3 if they're very brave. But we don't like in our defaults we don't use GPT-3. And by the way, so like just because GPT-3 is like the big one doesn't actually mean that it's good. It's actually not good compared to like Roberta and like Electra and stuff like that and Deberta. You can actually look up papers that show that when you have a fine tuning task, basically when you need to fine tune the model, those models are actually better than if you fine tune GPT-3. And beyond that, GPT-3 is just so ridiculous to fine tune. We are working though on actually, so we just added support for fine tuning on 20 billion parameter models, I believe. That's going to be in 0.6. But like, yeah, I mean, you asked like, is this not a monster? I would say it is a monster, but it's a tamed monster, right? Because so long as the user doesn't have to interact with the monstrous parts of it and it just gets the benefits, then it's, what is the harm really, right? What is the downside from the user's perspective, right? They're able to get the improvements from it and they don't have to deal with anything more complex than 3 lines of code. Right? Mm-hmm.
Thank you very much. Thank you very much for the interesting talk. I wondered how do you integrate images that are difficult to analyze, time series into tabular models.
I mean, so we do not mix time series with other modalities yet, if that's your question specifically. So like we don't work with video, for example, currently. We do have plans to, but is that like your question basically?
What are the challenges?
Oh, I mean, the challenge is just we haven't really looked into it. I mean, so like we have like a group of people working on tabular, a group of people working on multimodal, a group of people working on time series, and then just there's so much low-hanging fruit everywhere that we don't necessarily have time to look into all the combinations of all those things too at the time. But it's something on our thoughts. But like multimodal, right? We can support like you know, multiple images plus multiple text plus multiple tabular features at the same time, right? So like, I feel like that's a pretty large range of things, but is there like a particular thing that you're saying isn't covered in that?
Yes, my question is, what do you do when, for example, you have new raw data, like unsupervised?
So AutoGluon is not an
Like
unsupervised
images
learning
that-
framework. It's focused on supervised learning, generally speaking.
Sorry, I didn't.
Oh, AutoGluon is focused on supervised learning. So when you bring your training data, it should have labels. So we don't really work in unsupervised learning. That's an interesting area, but it's not as objective in the sense that it's not as easy to evaluate. And really, we thrive off being able to evaluate and iterate and detect if a certain version is better than another, which allows us to innovate faster. So we focus on supervised learning.
Thank you.
Thank you. I have a question. So you said that it's a type monster, users can easily use that, but is it still like one piece of the system? Maybe how easy is it to extend that, like not add another classifier or something like that, but really extend it with some fundamental functionalities. I mean, there are definitely some users that would like to have an auto Swiss knife, but maybe some people would like to have an auto toolbox, and for example, just to use the picture preprocessing part or just the unstyled parts.
Absolutely. So that's why the modules are completely separate pip installs. So pip install AutoGluon. AutoGluon isn't actually a repo. It's just something that installs all the different modules. So we have AutoGluon.features, AutoGluon.core, AutoGluon.common, AutoGluon.text, AutoGluon. Computer vision, AutoGluon.tabular, AutoGluon.multimodal, AutoGluon.time series. All of these can be individually installed and used. And so like AutoGluon.features, for example, includes all of our pre-processing functionality and is fully standalone. You do not need you don't need Hugging Face or Torch installed for that. All you need is, like the bare minimum, like scikit-learn and like NumPy and pandas, right? And then that's just the AutoGluon features. And you can use that in any other AutoML system, right? So if another AutoML system wants to say, listen, I don't care about the feature pre-processing, I just want something that works well enough and I want to focus on something else, then you can just, okay, I'm just going to use AutoGluon's feature pre-processing and then go from there, right? So yeah, it's modularized. It also improves our code sanity. If it's all just one monolithic thing, it's a nightmare. Yep.
All right, we had 2 questions. Sorry. We have to stop at some point. There's many questions, but maybe you can take.
Happy to chat later.
So thank you very much, Nick.
Mm-hmm.